quantum correlations and what are the peculiar features which show up. And all those questions are connected with what is generically called interpretations of quantum theory. Okay, that debate is not over, okay, it still goes on. But we just try to put various constraints on what that interpretation can be. So the whole subject actually can be tracked down to this one paper by Einstein-Podolsky-Rosen, which has the title, Can And this title basically says everything which is to be debated in this particular subject. Is the quantum mechanical description which we have verified by all kind of experiments, is it complete? Or going beyond, is there something extra? Okay. And all the ideas about hidden variables come from trying to answer this question, is there anything beyond? And in particular, what we are looking at, what are the constraints on this imposed by known even if there is something beyond, it should not contradict whatever is already verified. That puts all kind of constraints, and the whole exercise is trying to analyze these constraints and finding out what can be beyond within those particular constraints. And in particular, there are these two words which I mentioned, ontology and epistemology. Ontology asks that there is something beyond which you can't see right now, and epistemology says that whatever is observed, that is the end, there is nothing beyond. And you have to go back and forth between these two domains. And I should emphasize that Einstein had no problem with interpreting or looking at quantum theory as a empirical or effective theory. As a matter of fact, he made many contributions to quantum theory himself, which are quite fundamental, starting with the photoelectric effect, the specific heat of solids, then the spontaneous unstimulated emission, which produced the theory of lasers. Then there is a Bose-Einstein statistics and condensation. So all those features Einstein himself worked out based on the rules of quantum mechanics in whatever form. So he had no problem with that, but he was asking, beyond these rules, is there something extra? And that is where he was not very happy with the rules being as it is, he kept on arguing that there is something more. Okay? And whatever that more is, hidden variables. So now I discussed first the example of contextuality, which comes from operators not commuting with each other in quantum theory, and then how Bell bypassed it by using spatial separations of the measurements whatever context dependent situation there may be, because the signals are coming from two places which, because of the finite speed of light, are separated so that they cannot communicate. They have to be independent. Whatever is measured in one place cannot be influenced by whatever is going on in the other place. That is the guarantee by the spatial separation, and then you don't have to worry about the context. Those two are independent. And when you have an independent set of observables, you can easily say that what is the joint effect? It is a direct product because they are independent. And so total observable is just what is on one place times what is on the other place. And that gives the concept of what is known as a locality. So allows factorization now. You have to keep in mind that conservation laws will always be there, and quantum mechanics is not going to violate them. So there will be conservation of energy, momentum, angular momentum, etc. They are perfectly okay. There will be some correlations coming from that conservation laws, and they are not the ones which are going to be questioned. But locality means that what is happening in one place is independent of what is happening in another place. So you can factorize basically whatever property you want to look at, and then all these inequalities of the type Bell derived, they arise from a simple fact that I can write this observation as a sum over many possible configurations of the hidden variables. That sum can be rewritten by using the triangle inequality in terms of the absolute value. So the total value is bounded by the sum of all the absolute values, and that is just ordinary algebra, nothing to do with physics. And that bound, now if you consider that gives extreme values, in the sense that you worked out the result for all possible values of the hidden variable configuration. There is an upper value, there is a lower value, and then you perform any weighted average of it. The weighted average has to be between the two bounds. That is a standard rule of probability analysis, it cannot go outside. And this is essentially the content of Bell's inequality. So weighted average of configurations can be bounded. And this is nothing but triangle inequality. The trouble is that you follow this prescription, find some consequence, compare it with experiment, and this analysis fails. And then they can ask me, what is in the description which is wrong? Because experiment doesn't agree with it, so whatever assumptions you have made, explicitly or implicitly, something is not right in that. And all the questions or constraints about quantum theory are based on which particular aspect you are willing to give up in this whole structure. So I gave this analysis last time, which gave this the result which is proved in Bell's paper, where this is the expectation value of the joint observation of the spin or polarization in direction A at one place and in direction B at another place. The locality has gone in that I can write this correlation as the product of these two. Okay. Because whatever is observed at A is independent of whatever observed is at B. And then I average, some weighted average over all configurations which may be there, which is denoted by the expectation values. And this is a result which doesn't agree with quantum theory. And in quantum theory, we are going to look at the situation of this observable which will be just the qubit or polarization signal at one location and one at another location measure along two different directions. Now, you can write it in many different ways how you can evaluate it. I will just give a shortcut. So you can also write it as a sigma dot B doesn't matter, many different ways of looking at it. One way is this. These things are independent, so of course you can commute them, where what you call A and what you call B is immaterial. You can write it in either order. Another way of saying is this: in quantum theory, all these objects are going to be Hermitian operators. So you take a Hermitian conjugate of this, that becomes this. The order flips and polymatrices are Hermitian. So these two are the same, but it allows you to calculate the result a little more conveniently, because I can now write this thing just explicitly writing out the dot product. And the expectation value is only on the polymetric. Well, I can put it anyway. What I have done is just average these two. And since the orders are interchanged, I can write AI, BJ, and these things are flipped around. The point is, now you can evaluate this in many different ways, but writing this combination makes a life a little bit simpler, because this is non-zero for only I equal to j. There are the usual rules of multiplying polymatrices. And so this you have to evaluate, and you evaluate it in any way you want. This will be like I and j are the same. So this summation basically becomes a delta function. And when the two indices are equal, I'm going to evaluate it in the singlet state of the two qubits, where I measure any polymetrics eigenvalue. The two directions are antiparallel. So if I calculate this in the singlet state, there is a minus sign coming from it. And this dot product is just the fact that I is equal to j. If you are not happy with this much description, write down the whole wave function singlet state. It has 4 components, and these polymatrices are 2 by 2 matrices. Multiply them, evaluate by brute force, you will end up with this particular result. This is just trying to give an argument where you don't have to work so hard, but the answer is what this is. And now the trouble is that this result is in conflict with this inequality. So conflicts for the directions I kind of choose. A, B, and C was in the middle. You can choose many other possibilities for the vectors, but this configuration gives the so-called largest violation. So it's generally quoted because we want to test something, better to measure it where the value is maximum. Otherwise it is close to 0 and you don't get that good a signal, particularly where you are trying to do experiment. And this is essentially the content of Bell's inequality, and the singlet state is an example for what is known as untangled state. Okay. So this was all illustrated by John Bell very powerfully. But some of the words which are involved here again go back to these initial questions, and the same question was put much more in what you call a realistic example by Schrödinger. And Schrödinger actually responded to this particular paper, and he created an example of this particular type where there are correlations, and that example is what is known as Schrödinger's cat. The cat is alive or cat is dead, but it depends on some radioactive atom, which is it has decayed or not decayed. So there is a correlation between that atom and the cat being dead and alive, and then the question is, well, you don't know whether the atom is really decayed or it is still in the excited state, and depending on that, the fate of the cat is uncertain. How will you, what you call, understand that kind of scenario? But it is a same kind of situation. Two-body system, there is a particular correlation, and it gives something which is, well, doesn't agree with our common sense, just put it that way. But the word entanglement actually is contribution by Schrödinger, because he gave this example of this cat and then said that quantum correlations have this peculiar property, and he called this property entanglement. So that's where the word comes from, and I will just quote a generic result that any, I'm not going to give a proof of this, any pure entangled state can be shown to violate some Bell type inequality. So as soon as you give me some pure entangled state, just has to be bipartite state. Here it is a qubit, doesn't have to be qubit, anything of that kind. You can design a particular observable which will show this kind of violation of the inequality. So it's a powerful result. And then the question is testing this, okay, in real experiments. And that is what the Nobel Prize of last year was given for. And if you want to look up this historical context much more in detail, I wrote an article last year. It is on my web page after the Nobel Prize, and you can read it. It gives, well, some background of what all went as an input. But the version which was tested by the experimentalists was not this one. This required 3 axes, A, B, and C, and you perform measurements, but the axes are not so conveniently located in terms of being able to rearrange them in this direction. One of them is at some 45 degrees, etc. And you have to ensure this spatial separation, which means you should be able to flip the choices very fast before they can communicate to the other side. And that was not very convenient in this particular framework. So the version which is tested is an extension of this analysis, which goes under the name CHSH inequality, just the acronym for the 4 authors: Clauser, Hahn, Shimoni and Holt. Okay. But everybody just lists this thing as a acronym. So what it does is, doesn't work with 3 axes, but it works with 4 axes. And the 4 axes can be organized more easily for the experimental measurements. State is the same. It is still going to be 2-qubit singlet state. But we are going to measure 4 axes, and I will so what is the form of this inequality? I will write a little bit of shorthand to avoid all this notation, but it's kind of understood. So it has, I will just write A and B, ignore all these locations and probability and all those kind of things. So the combination is just this. Where A and B are this observables plus or minus 1, whatever it is. So yeah, because they are just some qubit observables, eigenvalues of the Pauli matrices, and you will measure it along some direction. You'll always get a plus or minus 1. So now you can rewrite this thing in a slightly different manner by factorizing this object. I'm not going to look at, so this is a check. So now I will not look the expectation values, look at individual terms one by one, sum over some configuration. So this can be easily written as A plus A prime times B plus A minus A prime times B prime. One particular set of measurement, and you will generate a whole lot of distribution and take weighted average after that. Okay. So individual contribution looks like this. Now what is the property of this under this particular choice? That they are between plus and minus 1. So it's very easy to say that either this one is 0 or that one is 0. There is no other choice. If A and A prime are equal, this one is 0. If A and A prime are opposite, then this one is 0. And when it is one of them is 0, what is the value of the other one? It is either plus 2 or minus 2. So this is either of plus or minus 2b or plus or minus 2b prime. Can't be anything else because of this specific values plus or minus 1. So one can easily now write a bound when you do a weighted average of all those things by whatever hidden variables you can think of. So you can assign any probabilities you want. Is bounded in this particular interval, because whatever b and b prime is, they are plus or minus 1. So whatever this side is, minimum value is -2, maximum value is +2. You do some averaging of various things, it will be in this interval. It can't go out. And that's it. It's the same philosophy which went inside here. The triangle inequality came in when you did this weighted average. This was just a simple identity because of this plus or minus 1. Nothing more than that is required. So those are very trivially bounded. Now you ask the question, what is the singlet state is going to do? Okay, so I am going to choose these directions of A and B, some configuration. Again, the configuration which I will illustrate is the one which gives the largest violation, because that is what people were testing, and it goes something like this. So there is A prime, B, and B prime. The angles are 45 degrees. But the point which is nice in this arrangement that A and A prime are orthogonal and B and B prime are orthogonal. That helps in experiment, because A is going to measure something. It are two choices. Orthogonal directions have a lot of advantage in terms of either a quantum analysis or even experiment. You have polarizers which can easily sort the orthogonal direction. So that is helps in experimental setup. Here the directions are not orthogonal, so you have to rotate by some angle which is not that convenient. So now what is the answer? Okay, we'll work out this thing. The result is already here. The correlation is in the singlet state is the dot product with a negative sign. So you plug in the values. And so A and B, this is 1 by root 2, well, there is a negative sign, so okay, doesn't matter, I will put it here. The next one is A prime B, then the third one is AB prime, which is again 45 degrees, and then is A prime B prime. This is different because this angle is now 135 degrees, and the dot product is minus 1 by root 2. So with a negative sign, this is 1 by root 2. So this value is, well, 3 of them are opposite or same sign. This fourth one is different, but it has an opposite sign over here. So it is there's a negative sign for whatever the reason. Went out.
That representation of this representation of sigma, like, this essentially means that sigma is acting on here and sigma.
Yeah, so what you are doing is the measurement of this polarization. I am writing this same thing as a shorthand. Yeah. So this is violets. So now, I mean, this was essentially what was done, an experiment. So there was a source and which sent out these correlated photon pairs in the singlet state, and there was one observer on one side, another observer on the other side, A and B, and they had these polarizers. So 2 of them you have to put whatever it is. So these are some directions. Polarize, it's a measurement actually. And what you need to do to make all the constraints true is that you should be able to choose this polarization direction at a rate which is so fast that that flip-flop between here takes less time than the time to travel for the light between the two places. Okay. So because then only you can take advantage of the spatial separation and say whatever is happening here is independent of whatever is happening there. So you have to have these filters which can be flipped back and forth at a very high rate, but this is typically experiment on tabletop, and the distances are, say, in meters, and so the time for the travel is some nanosecond, something like that. So you have to flip-flop this thing so fast that this one doesn't know what is happening over there. Okay. So that was the experimental achievement. Actually, the first test which was done by Clauser, that is also an interesting story, that he measured this thing, but just by setting the filters in this direction, but no what you call constraint about spatial separation. He just measured the 4 terms one by one, or here in case of 3 terms one by one, and found that yes, it is violated, but that had not checked that there is a ruling out of any correlation between these two, and that part was subsequently carried out by Aspect, who is the other winner of the Nobel Prize, and they made this arrangement so this thing can be flipped very fast. Incidentally, Clauser is a same person who derived this inequality and also did the experiment after that. When he contributed to this inequality, he was only a graduate student. And when he checked the experiment by measuring the terms one by one, he was a postdoc. He didn't have any money or anything like that. So the first experiment they were done, it's an interesting story. It was done in the basement in a Berkeley lab by all kind of parts which were taken out from discarded equipment. So there are people who had some old machinery that were loose, dismembered it, took out various parts and assembled in the configuration which he wanted, and then some things were still missing. He borrowed it from some lab for a few days. Okay, give me this so I can do this, I will give it back to you. And that is how that experiment was done, and it basically checked that all the terms are as expected, but one by one. And that loophole of ensuring the spatial separation, that was filled by Aspect, where he literally designed this kind of sources. It had to be at a fast enough rate to generate enough statistical sample, and rotate these filters also very fast. Now, that was still not enough in the sense that I'm going to rotate these filters and I will choose these orientations randomly. But then how are you going to create random numbers? Or that mean every time you are not going to toss a coin. Okay, it takes too long. You need it at whatever gigahertz rate or something of that type. So they use whatever the conventional computer-based prescription, some sequence of random numbers generated, but people could argue that they were not truly random. So the Zeilinger, who is another winner of the Nobel Prize, he even went further, that he could, he improved all those things. Rates of the singlet sources went up, the detection efficiency went up, all those questions you have to answer. Because the photons are created, but the first attempts of detection, the efficiency was not high, only some 10% or something like that. And so when you argue about this, maybe you say the 10% of the time where you measured the results were correct, and the other 90% time it could be something else. You don't have enough confidence. So that measurement accuracy also had to be improved to more than 90% or something like that, all those kind of tricks. But Zeilinger also did something more, that he decided these random numbers by taking signals as a light coming from some distant galaxy. So the light from one galaxy provided the signal for this polarization setting, and light from another galaxy provided the signal for this polarization setting. The galaxies were millions of light years away, so then you can say that okay, there is no correlation between whatever is coming from that particular light source. So they're all steps to remove any kind of gap or a loophole in this particular setting, and ultimately it all came out that yes, the results are not changing, and you could use these things. So the random behavior can also be ensured. So randomness can be from and it all worked, and now the result is so strong that there is so many sigma deviation, and the probability of this thing being wrong in any sense is basically infinitesimal, less than a billion or whatever number you want to put in, you can verify it to that particular level. So that is experimental part, and this all worked. Now comes the question is, we accept now this as a fact. What does it tell you about the original questions? Yeah.
Suppose we assign A, B, A dash, B dash, and then we consider the ensemble.
Yeah.
In the ensemble measurement, like in the left part, for the A part, capital A part, half of the measurement should be A and half of the measurement should be B, right? But that order is random. That's what you're saying? Or?
Yeah, so it's doesn't have to be exactly half and half. It can be some weighted average which all can be normalized. Because each of this is expectation value depending on the number of events, you can normalize it. In experiments, it means not exactly, you can call this one is N1 and this one is N2, then you have so much data, so whatever the data has, this part you divide it by N1, whatever is this one is divided by N2, and then the normalizations are made the same. And you can combine them afterwards. Okay.
Sir, what was the issue or the problem with the three-axis measurement,
sir?
Three-axis measurement, what was the problem?
The angles, I could arrange them very nicely over here, and that made the experimental part easy. There's nothing wrong. I mean, the answer is all the same. The question is how will you measure these three things, and you have to arrange for all this polarization being flip-flopping very fast.
So the polarization flip-flopping seems to be mechanical, right?
No, what is done is actually, this is arranged by a beam splitter. The instrument is not moved, but the beam splitter will either put it in this or put it in that. And that beam splitter is rotated very fast. Because I mean, these detectors are big objects, you are not going to flip-flop it, but the beam splitter you can flip very fast between two orthogonal directions. Yeah.
Beam splitter or reflector? We need reflector or beam splitter?
Splitter, it has to sometimes go here and sometimes go there. So it's called a polarizing beam splitter to be more specific, depending on the direction you want to choose.
But then if we consider the 50-50 beam splitter, then we get the half of ensemble.
Yeah. So there is an ordinary beam splitter, but there is also something called a polarizing beam splitter. And the polarizing beam splitter sends one polarization this way and the other polarization the other way. What they use is this polarizing beam splitter. So the quantum theory all worked.
So here the single state would be in terms of polarization, vertical and horizontal.
Yeah, the experiment is done with light, not with spins of electrons. Yeah. Again, light is much more easy than controlling than electrons. You can talk in both languages, whatever you mean by polymatrices, etc. But it's experiments with light are easy. Also because transmission losses are much smaller. We want to send the signals, should reach there with high probability. So we, based on this experimental data, accept that our quantum description is correct. Then you come back to the question, what constraints do this impose on whatever the hidden variable you want to think about. So there are various what you call ways out. You want to give up something in this analysis, some step which mathematically is not in question, but physically you can say, okay, this is not justified. So some assumption must be given up. And there are many candidates. People have not stopped in letting their imagination go all over the place. One of the most quoted assumption is locality is violated. Sometimes this is also called Einstein locality, because that is what the description of this physical reality meant as far as Einstein's arguments went. What does locality violation mean? That I could write my observable as a product of two things. Because they were at different locations, I could consider them as independent, and then this whole analysis goes through. If it is violated, I cannot write this thing as a product of two independent objects. Okay. And then it's fine, the derivation fails, but you have to do much more than that, and the best thing is to construct a theory which agrees with quantum mechanics, but in which locality is violated. And historically, this theory was already present when Bell gave his theorems, and it is due to these two people, de Broglie and Bohm. Bohm was actually one of the persons which gave this singlet state as the correlation to be tested in quantum mechanics. The same person, he has also helped in construction this theory. It's non-local in the sense that the quantum state is defined by a distributed wave function. In quantum theory, a wave function is spread out over a certain region, but here they redefined it in such a way that you can talk about those two objects without using the language of the Hilbert space. And what they essentially did was break up the wave function in two parts. One of them was amplitude, the other is a phase. The amplitude is described by something which is local, but the phase is something which they made non-local. So it's also called a pilot wave theory. So amplitude, local, phase. Non-local, the non-local phase you can't observe. In general, that is true in many of these quantum description anyway. So the phase is there, which is non-local, but you can't observe. But the amplitude is local, you can measure it and you can observe, and then the results come out, and the results exactly reproduce all the predictions of quantum theory. Even though this theory has this non-local observable, and that is, well, it ends the argument in a certain sense, because it shows that you can get all the quantum physics by constructing a theory which is non-local in some variables. It's just an explicit example, and then you have to take it at that particular value, and people keep on still worrying about this theory, all its predictions. There is nothing mysterious in the sense that it's exactly equivalent to quantum theory. You don't get anything extra, and they just have a different interpretation of what objects belong where. And the phase non-local means that whatever is happening at A and B, no matter how far apart they have correlated phases. Once you do that, then there is no conflict remaining at all. Okay, so this is the commonly quoted result, that Bell inequality tells you that the locality is violated, or in other words, hidden variables are non-local. You can construct a complete description provided these hidden variables are made non-local, or at least some of the hidden variables are non-local. The next version goes under a little bit different name, and it has again all kind of other names which I'm not going to the names I'm not going to give, but the feature is that statistical independence of all these observables does not hold. What does it mean? That the observations they depend on the measurement settings. If you allow for such a big step, then you can do anything. that whatever you are observing is a function of your measurement setting, and I just cannot say that they are all this plus minus 1 kind of thing. If I had chosen A, then it will decide how often it is plus 1 and how often it is minus 1. And if I choose A prime, it can be again a completely different set of values. Then the whole structure basically breaks down, and people can cook up all kind of scenario which this is just one example how you can have such a situation if the signal somehow goes back in time. Nobody really wants to worry about this kind of thing because you have then trouble with causality and all kind of situation. But the kind of scenario is this: when A measures something, its signal goes backward in time all the way to the origin of the singlet pair, and then it goes forward in time to point B, and it will change something there. Looks weird, but you can cook up scenarios like this, and there is no escape from this. If you are going to violate some principles of this type, that what you measure depends on the status of your apparatus in some complicated way, all the analysis can be modified to give whatever you want. So that is another sort of escape. You just have to be a little careful that that correlation is not the same as, to make physical sense of it, you don't want to land up in trouble with causality. So people have invented various kind of scenarios where you can separate what you mean by correlation from what will be the cause. So if there is a cause, it will produce some correlation. The other way doesn't have to hold. If it's some correlation is observed, doesn't necessarily imply that there is a common cause. And quantum mechanics is thrown in that particular label, but fine, there are a whole bunch of candidates of theory of this type. But the part which is the least obstructive in terms of whatever has been constructed is the usual one, that the weights in averaging are not probabilities. You constructed an ensemble, averaged it. All these things are kind of bounds. They relied on the fact that I can say this, provided all these weights are in between 0 and 1, so that whatever I take the value, it will not go up from something else, this overall constraint. But if the weights are not between 0 and 1, then I can go out of this interval. And that is what is usually present in all the quantum description in different versions. So classical description is how you calculate expectation value. take individual event, probability of that particular event, and add it up. And these are all positive with a constraint that all of them add up to 1. Now, what is the quantum analog? We have seen this many times. It's a weighted average with the density matrix. It has similar constraints, so normalize. Trace of rho is 1 and eigenvalues. Are all positive. But these two are not the same still. Because how many objects, when you look at it, if you have a n component state, there will be n probabilities, but this is going to be an n by n matrix. And the diagonal form, if you take for rho, then the diagonal basis, the diagonal elements are exactly the probabilities because they are eigenvalues, they add up to 1. But it can be the situation where there are off diagonal elements. Okay. That will depend on the observable. Because if there is a basis in which both of them are simultaneously diagonalized, you will exactly come back to this. But in quantum mechanics, which can give us situations where the density matrix of the state and the operator which you are measuring, they do not commute. And then there is no common basis in which both of them are diagonal. So you can choose in rho can have off diagonal elements in basis that diagonalizes O. And typically in all the measurement analysis, we work in the basis which diagonalizes O. Because we'll say, what is the eigenvalue that is observed? Well, it is one of the eigen directions of O, and the state will end up in that. That is what you use in the projection postulate all the time. When you measure A, you'll get one of the eigenvector, and the corresponding eigenvalue will be the reading on the apparatus. So you work, all the measurement analysis works in the basis in which O is diagonal. But in the same basis, rho can be non-diagonal. And whenever that happens, you can expect something extra. Because off-diagonal elements of rho are complex numbers. They are not going to contribute with a definite positive values, but they will come with phases. And they certainly go out of the bounds with a plus sign and minus sign, or more generally some complex phase being present. And if you try to now look at what really happens in all these inequalities and the kind of geometries which are used to detect the violation, you will notice that this configuration or this configuration, whatever it is, the directions which are chosen are not orthogonal and not parallel. If you have either orthogonal direction or parallel direction, you will end up in the diagonal basis. But when the directions are neither of those two, some angles, and all of them in these examples had some 45-degree angles. That gives actually the maximum violation. You don't want to be parallel, you don't want it to be orthogonal. Half the way in between actually gives you the best result. So violation here is the directions in whatever measurement directions. These are the basis of this O. Because when you diagonalize O is a Hermitian operator, it automatically gives an orthogonal basis. You want to go, not stay in the orthogonal basis, you get something outside. So these are not orthogonal, and parallel is just a trivial case. And this is how the quantum theory lands up with this particular description. And if you are willing to do this kind of a job, that I am going to give up the distribution of probabilities in favor of a distribution given by the density matrix, you don't need anything more. You can ask the next question, how is nature going to produce this kind of density matrix? That's a different story. But at least all the arguments of this inequality, etc., they are completely satisfied, assuming that the density matrix is whatever it is. Just take it as a fundamental quantity, and everything which you can measure in experiment, it always follows from this particular rule. If you do that, then you don't have to worry about any other implication. So rho is a generalization of classical probability distribution. We are replacing this formula by this formula. If you do that, nothing more is needed. And this is, in some sense, a minimal thing which you need to put in the theory to take care of all the questions of interpretations. Of course, these other things are there, they are not ruled out, but these are just possible descriptions which are all consistent with the questions of hidden variables. So in this case, you don't need any hidden variable. You said I'm going to replace the probability description by a density matrix, and that's the end of the story.
The statement should be locality is not all the things. Because the assumption that locality is not violated, we are giving it up.
You need to violate locality to construct a theory which agrees with quantum mechanics, but doesn't follow the constraints of this Bell inequality.
So the locality is not violated must be given up. Written the assumptions which should be given up.
Yeah, okay.
So it's a little.
That is what the hidden variables are non-local in these new theories. Yeah.
And regarding the second point also, the statistical independence does not hold. That should be true or it should be given.
Yeah, so it basically tells you what is the point which you want to throw away. So in this case, you throw away the assumption of locality. Here you throw away the assumption of this statistical independence. Here you throw away the assumption of a probability distribution. Put something else in its place. You can change the grammar of the sentences a little bit, that's okay. Okay. So this is story of these correlations, but that's not the complete end of the subject, and people tried to construct different scenarios where instead of this inequality you will have something else, some other kind of situation, and where again you will find some violation. Okay, so those are the things I will come back probably more detail next time, but let me give one version which is different than this correlation. Correlations are always some two-body objects. So this is the framework of Leggett-Garg inequality. It's a correlations between two, or rather not two, it can be many, between measurements on the same system. So there is only one system, but at different times. Here they're all bipartite systems. And I asked what is here versus what is there. And they were separated by this spatial separation. So here the correlations are in time. Okay. So here the space part was included by saying that if the distance is large, I cannot communicate and the measurements are independent. In the time correlation, you can always go back and forth. It's not constrained by any finite speed of light or anything like that. So you need some other equivalent set of assumptions under which you can derive some constraints, and as we'll see, quantum mechanics is going to violate those things again. So this set of assumptions It goes under the name which is macrorealism. There are 3 of them. So the first assumption is kind of trivial, that the system is in one of the allowed states at any time. Not only when you measure it, but irrespective of your measurement, at any time it will be, in this particular case, a qubit. It's either up or down. There is some probability for those being the 2 choices, but it's independent of measurement. That is the assumption which, in this particular case, consistent with physical reality. That whether the observer is there or not, the system has some state. Not only when you observe it, it gets some state, but irrespective of it. The second assumption is that measurements perturb the state only to a small extent. This is something different than quantum theory. In quantum theory, we say that measurement, we perform, the state gets projected. Here you assume that the system is more in the classical sense, you can perform a measurement, still it is more or less in the same state. And the third is future measurements do not or cannot influence past results. If you have measured something on a system, at this instant you got some result. If you go something measure in the next time slot, you get some other answer, and that second measurement cannot enter in the backward time and change the result of the first one. This is basically causality, that yes, once it is measured, the future is dependent on the past, but the past cannot depend on the future. And these are the set of constraints or conditions, and what this inequality shows. This is violated by quantum mechanics. If you assume all these 3 things, they will find some state which there will be a conflict. And again, it is derived in terms of certain inequalities based on these particular properties. And that means you will have to give up one of those 3 things. Again, it is your choice what you want to give up, etc. But we will see. The quantum features will come in the description when you try to calculate various things. And well, the analog of the minimal assumption of this kind of scenario of density matrix will be that the first assumption is thrown out. The system is not in a definite state until you measure it. But there can be other versions of it, which is, well, people keep on making up different scenarios. So the object which is constructed is again a correlation function, but now it is a correlation function in time, which I will call it as a, say, C I j is equal to expectation value of some operators, measurement operators, which I'm going to call Q. It doesn't have to be the same. So this is one at one instant of time. This is at another instant of time. And in case of our usual qubits, there will be polymatrices, nothing more than that, which you measure and then check the combination, which is three instances of time: correlation between 1 and 2, correlation between 2 and 3, and correlation between 1 and 3. And yeah, I will give the classical bound. The quantum discussion is for the next lecture. That is fine. So, classical. This Q of Ti is a measurement of just a qubit. This is a 2-level. So the values are only plus or minus 1. Nothing complicated. This is by essentially construction. And there are 8 possibilities, because there are 3 values of time. First one is a plus 1 minus 1, second one plus 1 minus 1, third one plus minus 1. You can just explicitly list them. Okay, and then are bounded, whatever it is. These 8 possibilities you just can construct. The way it goes is if both of these are same, 1, 2 is same, 2, 3 is same, then this one will guarantee to be the same, so it will be 1 plus 1 minus 1, that will be equal to 1. It cannot go more than that. And the other one is, say, 1 and 2 are not equal, but 2 and 3 are equal, so then the values will add up in different ways. And the worst case comes from the lowest bound, that these 2 are not equal, these 2 are not equal, but these 2 are equal, which gives a minus 3. So that is nothing they all you just assign whichever one you want and calculate 1, -1, +1, whatever it is. You can't go outside that.
Will there be not any,
Hmm?
will there be not any constraints from the conservation laws?
No.
But they are universal conservation.
You have the single system. Conservation law came from having two parts. And then the global quantity, like sum of this plus that.
Okay. So temporal.
Here is the time correlation. And so any weighted average is in this interval. The same logic as whatever write in there. We calculated for all the eigenstates. Eigenstates are all plus or minus 1. Listed all the values. And then any superposition or any combination of eigenstate you take, well, it cannot go outside the interval. So next time I will show you how it is violated in quantum mechanics. You have to choose the polymetrics here. Again, the directions will be such that they are not parallel and they are not orthogonal. Somewhere in between. And then we'll show that that particular configuration goes outside this interval. So that is a similar exercise, and I will work it out the next time.
This assumption should hold for every theory. These future measurements cannot influence past results.
Yeah.
This should hold for any theory. This assumption.
The principle of causality means
So it's
once you have something in the past, from the future you cannot go back and change that.
so only one and two are violated by quantum mechanics, right? Not all the three.
Actually, you can do this to a very good extent in quantum mechanics. You can design measurements which perturb the system only very slightly.
No, sir. The causality. Third one.
Yeah, third one is not violated in quantum theory. Yeah.
So the specific construction of AB, A dash B, AB dash and minus A dash B.
Yeah, one of the sign is negative. That has to be there.
I mean, so is there any specific rule for the pluses for those three terms and the minus for this term? Or like here also it's C12 plus C23 minus C3.
Yeah, they are all connected in some manner. You have a systematic procedure of constructing more complicated correlations by following certain rules. Yeah.
This is not the unique way of constructing HF, right?
Hmm?
This is not a unique way.
It's not a unique way. As I said here, that you can take any pure entangled state and find a corresponding inequality for it. There are lots of them.